Good morning. Yeah, good morning and happy Thursday, everyone. Hopefully the meeting is going well for all of you. It's a very busy week. So we're very excited for a number of different items in our schedule this morning. We'll start with Matt, who will be introducing the poster competition outcome. Thank you.
All right, so I'm Matt Zettergren, and I'm the one of the head judges for this year and last year and the year before. So I've done this a few times. And yeah, it's my pleasure today to introduce the 2024 CEDAR Student Poster Awards. Before I announce the awards, I'm going to go through a couple of things so that to maybe explain the process a little bit. And if you've been to this meeting the past few years, it hasn't really changed a whole lot. But first, I just want to acknowledge the number of students that participated in this year. So for Tuesday, which has historically been mesosphere, lower thermosphere, we actually have a mix of MLT and IT, ionosphere-thermosphere posters this year. We had 53 posters. And on Wednesday, we had 52 posters, and those were IT. So there were two poster sessions, 2 days of judging, and we picked two sets of winners, and they're loosely Tuesday and Wednesday. You can think of them kind of as MLT and IT. So I just want to pause here for a minute and just acknowledge the very high quality of all of the work that we saw students present. And one persistent comment I got from judges is just how impressed they were with all of the material that they reviewed. So I would like for everyone to give a hand to our students who participated. Okay. I very much view this, to me, the poster sessions and the student posters are sort of the crown jewel of the CEDAR workshop, or one of the very awesome things that I look forward to every single year. All right, the other thing I want to acknowledge, I've got a string of acknowledgments here because this is not something that I do. This is something that a bunch of people help me do. So I'd like to acknowledge the judges for Tuesday and Wednesday. I'm not going to call the names out, but I think we should at least acknowledge that these people devoted about 10 hours of their day to judging posters and participating in the deliberation and debate. So maybe a round of applause for the Tuesday judges. So those were MLT, IT, and yes, I'm going to make you applause again for the Wednesday judges as well. So thank you. If you volunteered, it's always a challenge. We have so many posters, and it takes a lot of time to review them. If you have served as a volunteer, thank you very, very much. And if you have not served as a volunteer, please consider volunteering next year. This is a very important process. We take this very seriously, and we think that the students do too and benefit from it as well. And lastly, I just wanted to thank Ling and Maggie for helping us deal with all of the poster submissions, getting everything organized in a spreadsheet and in a way that it could be judged sensibly and easily. So please thank Ling and Maggie. Okay, I promise I will present the awards in a minute, but I just wanted to say for the students in the audience a few comments about the review process, just so you know when you pick up your evaluations what it is that you're looking at and how it was used. There are 2 rounds of scoring for the poster competition. In the first round, the judge will review your poster without you there. Typically, they download it and look through it, or they walk into the poster room before the session and spend time reading through it. And then we have a set of criteria that apply to that. The round 2 judging, which is done by actually a different person, so every poster gets seen by at least 2 people. The round 2 judging is done. Oh my gosh, I'm so tired. Is done during the poster session, and in that case, the round 2 judge is actually speaking to the student and asking them questions and interacting with them. And there are actually different sets of criteria. So when you pick up your evaluations, you'll notice that there's the round 1 and 2 scores are going to be different, but they're also judging different things. I also make a quick comment that having done this for several years, I tend to notice certain trends that appear. And I will say that the round 2 evaluations are always consistently higher than the round 1. So the judges definitely appreciate the in-person presentations. So just a comment, and I don't know, you take that how you will. So after the 2 round scores are obtained, we average them, we produce a finalist list, we discuss any inconsistencies that we see in the scoring. This is, there's no way we can not make this small number of statistics in the evaluation. However, we do try to look at inconsistencies and resolve those as best we can, usually by discussing them for quite a long time. We look at the posters together as a group. We find our finalists, and then we rank order vote them in some sense. So usually we'll pick 8 to 10 finalists, and we go and look at those again, usually on the large computer screen in the judging room, and make a decision about first place, second place, honorable mention, and then undergraduate award. Okay, so if you've been to CEDAR before, you probably know all this, and none of it has really changed. I guess the only other thing that I would say here is regarding the forms and the feedback. If you're a student and you're looking at it, there are different, one thing we have to deal with the judging, they're different, everyone has a different normalization for their grading and scoring. And so I think, judges are encouraged to actually write written comments as well, so the students can sort of understand what it was that they liked, what they thought could be improved, and so on and so forth. And I think, like any form of feedback, you should look at it critically. You are probably likely to get something useful from the feedback, and you're also probably likely to not agree with all of it, and that's normal. That's part of the scientific process. As I said last year, and I don't always agree with all of the reviews I get on my papers or proposals. That's just part of the scientific debate. And so please try, if you're a student, try to interpret the comments as positive and trying to help. And yes, maybe the judges missed something, but it's also probably likely that they have some interesting feedback that might be helpful for you in the future. That's kind of the way I try to look at my proposal reviews too. All right, pick up your evaluations at the registration desk, and now I think we're going to get to the awards. So I'm going to start with Tuesday, do MLT IT first. And so as I call out your name, students, please come up here because we want to take a picture with all the poster winners. And Federico is going to hand you, did I give you those in the right order? I hope so. Federico's going to hand you your award, and please come stand on the stage until the end of this talk, because Leeing, I think, you're going to take a picture. Someone's going to take a picture. All right, we will have a record of this. Okay, Tuesday awards. I'm going to start with the undergraduate award, William McClung, for investigating connections between tropical tropospheric convection and thermospheric intraseasonal variability of wind and temperature profiles. I will note, as Federico hands his student a poster award, we do handle conflicts of interest. If you are conflicted on a poster, you are not included in any of the discussions or judging whatsoever. So just making note of that. Yeah, come stand on stage if you don't mind, please. Yeah, because it's just easier to get a picture with this later on. All right. So honorable mention is Alexander Massoud, two-dimensional UHF radar studies. But, congratulations. All right, second place is Ben Martinez from Clemson University. All right. Photochemistry versus dynamo as drivers of day-to-day variability in the ionosphere. And then we have first place, Sarah Lutkin from Colorado Boulder. All right, so those are our Tuesday awards. Now we're going to move on to Wednesday. I don't know, you looked like you wanted to. Oh. So thank you. So undergraduate award for Wednesday is Patricia Zwill. make sure you hand them the right one. All right, let's keep going. So honorable mention, Anton Binovsky. And I apologize in advance for pronunciations. If they're off, you can feel free to correct me. I really don't mind. All right, second place, Jose Maria Gomez Socola. All right, and first place for Wednesday is Madeline Evans. So, congratulations, students. You all did a wonderful job, and even if you didn't win an award, you also did a wonderful job. So one last round of applause, and then don't move, because we need to take a picture. All right, that is, did we get to, oh. All righty.
Thank you, Matt. That was very nice to see. Very nice posters. I was one of the judges, and I was very impressed by a lot of the work that the students have put in. Next, we have a talk by Devin about ASCAT, and we look forward to updates on the also 3D capabilities from ASCAT. Thank you.
Thank you, and congrats again to all the students who presented excellent posters the last few. Is this better? Okay, good. So yeah, my name's Devin Hugobert. I'm a researcher at UIT, or the University of Tromsø. I'm not directly affiliated with ISCAT, but I've received their blessing to give this update on the novel ISCAT 3D system. Let's see here. All right, so ISCAT consists of multiple different countries. There's China, Finland, Japan, Norway, Sweden, and the United Kingdom, who are all associates in the ISCAT organization. There's also different institutes or organizations that can join as an affiliate member, and these are shown on the right here as well. So each associate member puts forth members to the Administrative and Finance Committee, the Science Advisory Committee, and the Council. And then these councils provide guidance to the director on where ISCAT should put its focus as far as the radar systems. So the current ISCAT radar systems are located in northern Norway and on Svalbard. Here, and so on Svalbard, there's a 32-meter steerable dish, this one here, and then the 42-meter field line radar dish over here. And then just outside Tromsø, in Norway, there's also two incoherent scatter radars, the VHF system shown here, and the UHF system shown here. So one of the unique things about the Tromsø site is that we can actually make measurements at both frequencies at once, at 224 megahertz and at 930 megahertz for incoherent scatter radar measurements. So for those that don't know, this is a quick 1-minute slide on what is incoherent scatter. We're transmitting megawatts of power up to the ionosphere, scattering from the plasma there through Thomson scatter, and then receiving the signal and using our measured spectra, shown here, to derive the plasma parameters that gave us that spectra. So here we have the iSCAT Svalbard radar, transmits a signal, scatters from plasma in the ionosphere. We receive that signal, we use this spectra to derive electron density, ion temperature, electron temperature, and ion velocity. And so here's actually from the May 10th storm. The Svalbard radar was running for 96 hours straight. So that data is all available on Madrigal. So if anyone wants to take a look, the 1 minute data or 1 minute resolution data is available there. And Svalbard's somewhat unique as it provides one of these isolated data points in the polar cap that can be used for comparison with models and simulations. So iSCAT-3D, what is iSCAT-3D? It's a phased array radar system that's been in development for approximately 20 years now. So here's a illustration of what it was expected to look like. So this was developed by our Japanese colleagues at NIPR. And so each of these panels has 91 antennas on it, and these 91 antennas are combined into a data stream, and then that data stream is then, or a voltage stream, and then that voltage stream is digitized. So we digitize each of these panels individually, and so we can do some quite unique experiments because of this. It's a software-defined instrument. It has multi-user capability, so we can interleave experiments, or say 2 people request experiments at the same time. It can rapidly switch between pulses or locations in the field of view. One of the ideas is that it's modular, so it's easy to expand to new antenna fields. So the initial proposal was for 4 remote receiver sites. Right now we'll have 2 remote receiver sites, which is shown on the right here. So we have Tromsø, or just outside Tromsø and Skiboten, which will be the transmit and receive site. And then in Kaisaniemi, near Kiruna in Sweden, we'll have a receive site. And at Karesuvanto in Finland, we'll have another receive site. And so it's tristatic. We have 3.3 megawatts of power, and it operates at 233 megahertz. So what can we do with this system? I'm not going to cover too much on that, other than there's a science white paper and a publication about all the interesting science that can be done with iSCAT-3D. So I do want to highlight something that was shown in this paper, or highlighted in this paper, of some of the advanced capabilities. So one of these is that previously iSCAT had tristatic capability, but they were only able to determine that tristatic incoherent scatter spectra in one location along that radar beam. Now, through phased array techniques, and since we're digitizing each of the panels on the antenna array, we're able to actually sample multiple heights along that transmit beam. So we get a full tristatic profile of ion velocity vectors along that, as well as incoherent scatter determination or measurements. Another really exciting capability is that we can combine the volumetric imaging capabilities, for example with Pfizer, and combine this with doing sub-beam or in-beam imaging. So we can simultaneously look at the medium scale or mesoscale structures by doing this volumetric imaging, scanning from beam to beam. But due to the design of iSCAT-3D, we can also look at these structures. This is a Kelvin-Helmholtz simulation using the Gemini model. And the idea is that we'll be able to make measurements of the incoherent scatter spectra down to 50 meter to 100 meter resolution. So we can combine looking at small scale structures and large scale or mesoscale structures over the radar field of view. And then the power. So many of the radars that are in operation now are on, say, a megawatt class. So initially, iSCAT-3D will be 3.3 megawatts of power, but then this will be upgraded to 5 megawatts of power and eventually 10 megawatts of power. So this is an order of magnitude improvement upon the current iSCAT radars. So this will improve our time resolution, so we can get measurements much more quickly over the radar field of view. So as far as the status of the construction, iSCAT 3D, it arrived on a ship in Tromsø in September 2022. And then the panels were shipped to all the sites. So this is the Skiboten site here, and then assembled over the next year. So all 109 panels are now assembled. So we have 91 antennas per panel, and then 109 panels here, and then housing for all the radar electronics. So everything's now installed as far as the outer shell of the radar. We have the antennas, the buildings, the power, and the fiber. So you'll see here, though, that the start permit is missing. And this comes down to, so here's where iSCAT 3D is. The land has been cleared. If we zoom in, we can see that there was some work done to stabilize the ground on this side of the array. But then upon further analysis, it was determined that this section to the west, it could be a problem area. So right now they're doing further testing on this area and determining if further groundwork needs to be done before the site can be signed over to iSCAT and then the electronics can be installed. I do want to highlight as well that this is how the sub-beam or in-beam imaging will work, is that in addition to this main array, there's multiple sub-panel arrays. And so this gives us very large, or up to 1 kilometer distance interferometry baselines. And those have been installed, the fiber installed, and the power installed to all the sites. So for initial operations, for testing, the idea is to have 7 transmit arrays. So initially, it'll be on the order of 600 kilowatts. Make sure that the mutual coupling is manageable between the panels and that it's possible to transmit, receive, and perform the beamforming. And then from that, it'll be expanded to the next ring and then up to 3.3 megawatts. Since the Skiboten site is still undergoing some analysis on the ground, one idea for how we can proceed with testing the system is to move one of these test arrays. So this array here has the full transmit receive capability. So we can transmit on that, receive on the rest of this array or on subsections of this array and start testing the radar system and how we can start managing the data flow from all these panels. And so this is in Kaisaniemi in Sweden. And here's an example of just using the receiver on 2 separate panels and doing a sky map with combining the panels for beamforming. There's also been the network installed. So here we have 4 terabit connections from all 3 of the iSCAT 3D sites. And then, so why it's implemented this way is that there were some security management considerations that had to be dealt with. So the idea is that each of these sites records the data and then it gets sent to a secure data facility where the data can then be processed and then distributed from that facility. So this diagram shows the expected commissioning steps moving forward. So right now we're here. We have the transmit and receive from the PET or the test array. And then one other thing that was realized is that the iSCAT 3D system can actually receive signals from the 224 megahertz current iSCAT VHF system. So we can start analyzing the data tristatically and actually start performing the analysis along the full beam through using phased array techniques from these remote receiver sites. So that's, right now, we're here. The next step is to receive on a single antenna array from the VHF transmitter. Then we want to transmit from the test array, receive on the Swedish 7-panel array. So this would be receive only in Sweden. And then we also want to transmit from the VHF to the Sweden array, transmit on the VHF to the Finland array, then transmit and receive on both. So at that point, we're at the tri-static stage along the full beam with the system. And then, of course, we want, when the groundwork has been verified, well, the electronics can then be moved into the Norwegian site, and then we can transmit from the VHF array to the Norway site. And then right now, it's considered that first light will be when we can transmit from 7 panels at the Norwegian site and then receive on those 7 panels from all 3 sites. So there's always the question, how do I get access to iSCAT data? What will be the plans for iSCAT 3D? So right now, there is open peer review time that's available. So the deadlines are the 1st of May or the 1st of November, and there's up to 200 hours experiment time per year. And so this is open to all international scientists. It just requires an application. And I will say that in the past, this has been underutilized. So if you're interested in incoherent scatter radars and want time on a radar system, this may be the way to go. So, and right now, this is only for the current iSCAT systems, which I haven't talked much about here, but I'll give an overview in the ISR World Day session later. All the different experiments, they're set up different than the Ikamarka and the Pfizer experiment modes, and there's documentation, for example, on the iSCAT website here in this experiments document on how those modes work. And if you're interested in what the current status of the systems are, there's actually a status update page on the iSCAT site as well that you can look at. I also want to highlight that recently there's been a really nicely done video on iSCAT. So it's about a 30-minute video, but it covers iSCAT, iSCAT 3D, and it has some appearances by researchers and professors from UIT and from iSCAT. So the future of iSCAT. So one thing I mentioned was that there are some security considerations with the data, and because of this, iSCAT is reforming from a scientific association to a company. So this should happen in early 2025. This company will be owned by the Finnish, Swedish, and Norwegian governments, but the idea is that there will be minimal changes to operations, minimal disruptions. There might be a few different administration steps for radar time, but we'll see what the new company ends up being once it's formed. And then, so progress is ongoing with the installation of electronics, and all the sites, the outside hardware is all installed, the power's installed, the fiber's installed. It's just getting that groundwork permit at Skiboden. Thank you.
Thank you very much. We look forward to the exciting science that will come out of these new capabilities from iSCAT. I think we have time for maybe 1 or 2 quick questions. Okay, I don't see any. Oh, I see one question. Oh.
Devin, thanks for the update. When you say this transmitter unit that is located in Finland, that has to be relocated because I understand there is no TR switches in the receiver, right?
So you're talking about the one in Sweden that's been installed, the test one?
Yes.
So there are TR switches in that one.
Yeah, but you want to receive in the receiver.
So that's only for one panel. So there's been one test panel with the TR switch that's been moved to the Sweden site to commence testing. So they can transmit on the one panel, and then the idea is to receive on the array.
Okay, thank you.
Yeah.
Let's thank again our speaker. Next, we are very excited for the distinguished lecture, which will be introduced by Jeff Forbes. Please.
Tough getting old and having your knees replaced. Well, it gives me great pleasure to introduce Jeff Thayer as the 2024 CEDAR Distinguished Lecturer. I'll just give you a brief biography of Jeff. So Jeff grew up in New York State, where he played high school and collegiate soccer, receiving his bachelor's degree in meteorology, magna cum laude, at SUNY Oneonta in 1984. Obviously, he did a lot of studying in addition to playing soccer. He then went on to the University of Michigan, where he received his MS in atmospheric science, and then the PhD in atmospheric and space science in 1990. His PhD advisor was Tim Killeen, and his thesis title was Neutral Wind Vortices in the High Latitude Thermosphere. After Michigan, he went on to spend 14 years at SRI International, where he directed the Sonderstrom Greenland Geospace facilities for 8 years. For the past 20 years, he has been engaged in teaching and research at the Department of Aerospace Engineering Sciences at the University of Colorado at Boulder, where he has received both teaching and research awards and graduated over 20 PhD students as their advisor. His present positions include research professor, professor emeritus, and faculty director of the Space Weather Technology Research and Education Center. That's also housed in our department. As many of you know, or all of you know, Jeff is an outstanding researcher. He's published over 120 papers spanning the spectrum of solar terrestrial physics research. He's worked on ground-based FPI, ISR, and LiDAR systems, IT general circulation models and theory, and satellite systems and observations. In service to the community, he directed a national LiDAR consortium for 9 years, chaired the CEDAR Science Steering Committee for 3 years, at which time he led a major strategic planning effort. He has served in numerous advisory roles for NSF, NASA, NCAR, AMS, and the National Academy. A little or perhaps less known aspect of Jeff's career is that he's an inventor and entrepreneur. He holds US and international patents in LiDAR technologies applied to semi-transparent media. He has commercialized LiDAR products to see beyond the surface for water bathymetric mapping, and co-founded Lightwave Technologies that was recently acquired. On a personal level, Jeff is dedicated to his family, which includes his wife, Chris, of 35 years, and 2 daughters, Casey and Megan. In his free time, I don't know how he has free time doing all this other stuff. He's enjoyed coaching girls, soccer, playing guitar, skiing, hiking, biking, windsurfing, and anything involving sports. So it gives me great pleasure to introduce my good friend and colleague, Jeff Thayer.
Wow, okay. Well, thank you, Jeff, for that kind introduction. And yeah, it's been a bit of a road. I do want to thank those others who were involved in my nomination. I greatly appreciate your support, as well as the Science Steering Committee's selection for me to represent some of the esteemed distinguished lecturers of the past. And I do want to recognize my wife. Chris is here today. She's also trying to figure out where my time goes, so she's here to see that. And it's been 35 years, 36 years this July, and you know, she's supported me through all of this, and a lot of sacrifice on her part. So I greatly appreciate it. Yeah, clap for Chris. Yeah. It's funny, this position, this distinguished lecture award, when I served as chair of CEDAR from 2007 to 2010, I proposed a distinguished lecture award to be established for the CEDAR community. So it sounds a little rigged, but I had no idea that I would serve that role here today. So, so in doing so, I did have a thought in mind as to why I would like to introduce that. We had a CEDAR Prize lecture, so we were recognizing people within the 4 years period, you know, of great results like what John Emmert gave on Monday. And, you know, but there were people in the field who have put in, you know, 10, 20, 30 years of effort, and I wanted to hear from them. And the things I kind of want to hear about, and the things that I'll talk about today, was their perspective, right? Because perspective, all the experiences they have, and just to convey that, it's hard to capture. You don't capture that in a paper. You don't capture that in a journal article. You capture that with the side meetings you have and the discussions you have. And so I think, you know, given that this is a family to me, the CEDAR community, that I can share my perspectives, my musings, which are definitely ones that are not written down, although now they are, I guess, in this talk. And then a concept I'm going to share with you about entanglement, which I'd like to run by you all. So I'm using this as an opportunity for that as well. So that's the outline of my talk, and I'll carry on. But I wanted to provide some evidentiary material to show that I have been a member of CEDAR for a long time. And I can't believe it. I keep doing the math on it, and I'm like, yeah, Simon, it's 37 years. You know, I'm like, it's just amazing. And so here's a letter I received from Barbara Emery when I was a student at the University of Michigan with Tim Kleen as my advisor. And apparently I was late in my registration. But 1987, I was, and it was declared to be the second CEDAR meeting. So there is some, I think this is pretty much 1986 is when the CEDAR meeting started. I think as Mark was saying at the beginning on Monday, and sure enough, I have evidentiary material here to show that is the case. There were 140 attendees. We're up at the Mesa Lab up in Ankara, which is a beautiful site. And that was part of my draw to Boulder, honestly, because it was one of the, I came from Ann Arbor and I went to Boulder. I did go on a ski trip when I was in high school with some friends, but prior to that, I had not spent any time in Boulder, and it was an amazing time. And I feel blessed every day that I'm able to be there today as a professor in the department. But so 140 people, we're up to 400 now. So it's shown great growth over the years. And 37 years of involvement. Another piece of evidentiary material is, this is actually, so I save a lot of stuff, and this is much to the chagrin of my wife, who says, you need to get rid of these things. But then this just supports why I keep them, because I found this in a folder that I had stored away and hadn't looked at for 35 years or something. And so, but this is an agenda from the 1993 meeting at CEDAR, of which I was placed on the agenda by Rich Benke. Now, here's the confusion that comes into when CEDAR started, because Rich Benke called this the 10th anniversary in 1993, which would make it 83. But that's because that was JBOA and the radar communities coming together at that time. And so I think that's where it led the confusion for the future. It was like, what year is it? But these names you should, these researchers really were the trailblazing people to the community. And they stuck me in the middle of all these esteemed people as a recent graduate of my PhD. And then they said, okay, and it's going to be a lighthearted look. I'm 3 years out of my PhD. I'm serious about what I'm doing. And they want me to do a lighthearted look of what I've been doing. I'm like, that's tough, because I really wanted to be serious. And the fact was that I received a CEDAR award. I wrote a proposal to CEDAR 6 months after my PhD, and that award was to build the Sonnenstrom LiDAR. So I was awarded that, and I had 2 years to build it, design it, to build it, deploy it, and operate it, and get it going. And we did it in 2 years. We got it deployed to the Sonnenstrom LiDAR facility, and it ran until the facility was shut down just recently, so 25 plus years of data collected with that system. But in that talk, I remember one thing. I had view graphs. These are plastic slides. For those that don't know what a view graph is, these plastic slides. And I was about to get up, and they're really slippery, and they slid right out of my folder. And they were shuffled, and I had to get up here and give my talk. And so that was my first introduction of trying to speak in front of a group like this. Fortunately, we have PowerPoint now, and that's not an issue. Anyway, so there's some great history, and I could go over that forever. But I do think that one of the things that CEDAR has really done for me and others and colleagues in this field have been so embracing of the students since the start. And it really makes for this sense of community and family and I just feel it that way. And I think it's just a great testament to all who are involved to recognize and support the students as they go forward. All of the transferable skills in a changing marketplace. Actually, I think the marketplace, Aaron, we've talked about this. I think it's pretty bright for students compared to when we were students, in the sense that we were looking at certain jobs. But now with the commercial market in this field, it's pretty amazing. Total access to researchers in the field. I did have a few cartoons, but I've held those back today about how you might interact with researchers in the field for students. And then the opportunity to present your research at various levels is always great. And it's essential for the future direction of CEDAR. Not so much that you're going to be a student and then a researcher within the CEDAR community. That'd be great. But I think the things that we establish within this group, within this meeting, are transferable, that they can take elsewhere and still have that indelible mark that CEDAR leaves on them as they go off and do other things outside of the CEDAR community as well. And so I really appreciate that. So I need to get into my talk. Perspective. Everybody has a perspective, and we should all be welcoming those varieties of perspective based on the experience they have. And this enthusiastic turbine prop engineer was really thinking this is the way that an aircraft should be built. And they must have missed a requirements review document a couple of times, but in the end, you want to capture that enthusiasm, right? And I think I need to. Everybody has it comes from experiences. Everyone has an opinion, but I believe perspective is built through experiences. And so for me, I've gone through this process many times. We think about what we're doing. Is it the right step? Is the wrong step? Whatever. And I'm not a big quote guy. I don't necessarily put quotes on the mirror and when I get up in the morning and tell myself to get going. But that's okay if you do too. That's whatever it takes, right? But But I have found over time that this quote, I was in my applied math class in undergrad, and this quote came, one of my applied math teachers brought this up because Norbert Wiener was known for a field of cybernetics and actually kind of the early days of AI, actually. He's an interesting person. You should actually look at him. I think he graduated with his PhD from Tufts University and when he was like 14 or 15 or something. It's a really interesting person to review. But the first line of this, the most fruitful areas of growth of the sciences are those between established fields. That kind of resonated with me. And then the last line, it's between these boundaries of science that offer the richest opportunities for the qualified investigator. And I really, this wasn't in my pocket since undergrad. I started to progress through my career, and this quote always came back, and it just resonated with me. And it continues to resonate with me. I put it in documents like the CEDAR steering strategic plan and stuff like that. And I do think it's really an interesting, it just helps me think about how I like to go about my research. And so I'm just going to give you a little bit of quick coverage of what I've been doing, because I'm going to give you my perspective, and I need to give you my experiences and background so you can see where I'm coming from. So really, my work has gone, I say from sun to mud, and it's literally from the sun to the mud. This paper that we worked on from chromosphere, ionosphere comparisons was really a lot of work and a really enjoyable paper to work with James Leake, Rick DeVore, and a bunch of others that you guys know on this list. And that was a chromosphere paper. None of this is chronological. This is more just from the sun, interplanetary medium, and then into the thermosphere, where we worked on co-rotating interaction regions and how they affected the upper thermospheric densities. The further transition, I spent a lot of time on. It's funny how some people like, oh, you're a LiDAR guy, or you're a radar guy, or you're you do joule heating, or you do Nautilus in clouds, and yeah, we do all those things. But I think that what I try to do is try to provide try to help along, be impactful as to what your science can do. This work was a lot of incoherent scatter radar work and a lot of interactions with folks to work on this paper that Josh and I wrote and has had an impact, and we've been happy to see that progress. I'll talk about some of the things in a separate slide about some of the thermospheric studies, as well as the things like helium and some of the distributions that go along there. So just to continue, I also work on a lot of satellite drag problems and orbital drag, and we've been doing that a lot lately. I work with Caitlin and Lynn on some of the planetary wave behavior in the middle atmosphere. And even we worked on global electric circuits problems. Jeff Forbes was the PI of this project, and we worked on a model for doing global electric circuits that extend from the surface all the way to the magnetosphere. So the Sonderstrom LiDAR was a big part of my life. I spent a lot of time in Greenland, a lot of time away from my family, unfortunately. But it was a truly magical experience, and sad to see that facility is now closed, but still open in my heart. I've also worked a lot on LiDAR systems of different types. We started to move down into the troposphere, so a lot of my students that you don't know are ones that have worked on tropospheric LiDAR, clouds, and things like that. And then I started to, we had a problem that we were approached by some folks to talk about, can you use LiDAR for bathymetry? And so we started to work on semi-transparent media and the propagation of laser light through that. We patented some stuff and put together a LiDAR system that can now map in shallow waters at high resolution underwater features like this jetty that fell under the water system and stuff like that. So yeah. So yes, I'm a soccer fan. So I did steal this patch from anyone who's an EPL fan, English Premier League. May recognize the team Arsenal. I took the A out. It's called the Active Remote Sensing Lab, but I used that patch. Tough year. We almost won it this year. We've got a great, my student put together a beautiful patch, and so we use this patch. So I have to credit all my students over the years who have contributed to this work. Obviously, without the students, I wouldn't be as far along with all the subjects that I work on without them. And some are recognizable, like Caitlin up here in Greenland by the ice cap. Some of the others are doing more LiDAR-based research. Robert doesn't mind me showing this picture of him sleeping on the ground because we could never catch him sleeping, so if we did catch him sleeping, that was a unique moment. He's actually sleeping next to the instrument as the instrument was running, so he never failed. And then, you know, some people have asked me, well, you're retiring now and all that kind of stuff, and it's like, I don't think so. I got a lot of students to get through the PhD path. Some I'm advising as an academic and research advisor. Some I'm an academic advisor. Like Arunima is working with Luis Navarro here. Robert is working with Ed Tiemann. You've met Anton recently this morning. You've met Sarah recently this morning. And then Austin is here as well, and the other students. And so it's going to be a fun ride to help them through the progression to graduation. So just for perspective purposes, you know, this slide is shown by many who want to indicate that your own experience doesn't provide the whole truth. And that's fair. That's a good thing to point out. And but for me, it's teamwork. You could see there's communication happening here between them, even though they're saying it's something different. They are communicating, and they are working together to try to figure out what this beast is. The thing you want to avoid is this person. You don't want to be that person. And to avoid that is to collaborate. I feel strongly about collaboration. This meeting is all about collaboration. And you just want to stay away from things that may not pan out. But when you look at the individuals on this, on the teamwork that's happening around the elephant, the next step that they're going to do, this is all in situ sensing, right? So they're all touching it. And so what they're going to do is they're going to start to move. They're going to start to move latitudinally around this unknown object and communicate what that information is. Then they're going to start to move longitudinally around this object, and eventually they're going to discover that this is an elephant. And this is what we're going to do as we put more and more things in the field, whether we're putting up GDC and using 6 satellites to determine the elephant. But it's this kind of teamwork thing that I really want to emphasize. It's teamwork that really, I'm not going to say it, but there's teamwork that really makes it go. And so I just want to give one example of that type of teamwork that I feel is relevant to this community. The CEDAR Strategic Plan, the New Dimension. This was absolutely a team effort. I know I get some credit for it. I wrote the foreword, and I definitely was involved in all the text and everything. But it was a team effort. And I have a picture here of the WHOI team. I want to recognize the steering committee members, 2007, 2011, who contributed to this document. The WHOI writing team, we spent 3 days. We were like, okay, we need to get this thing done. So we're going to hunker down, and we're going to take 3 days, and this was a great group to make that happen. It's so great when you talk about strategic planning and you're thinking big and everything. It's really exciting and fun, and I really appreciate it. Having a great illustrator like Vicki Moore from SRI made everything pop out of that document. That was so impressive. And then getting support from the NSF upper atmospheric folks like Rich Banke, Bob Robinson, Bob Kerr, and Farzad was all very required and instrumental. I just want to point out one thing about that document, and one, I want to explain something, because I want to make sure that where the title New Dimension came from. The title New Dimension comes from this added axis that we put on this diagram called complexity. And we introduced that because we see a systems perspective as one that can perhaps help advance the field. And so preconditioning, nonlinearities, instabilities, emergent behavior, feedback, these are all things that we know are present in our system, but they're hard. It's hard. It's hard to measure. It's hard to figure out. I actually think it's still in its infancy for our field to contribute to this, because we're so lacking in observations that we really can't get to this next level. But I think we need to get to this next level to be able to understand our stuff. So that's where the definition, that's where New Dimension came from, just to share that if it wasn't clear in the document. Okay, great. So So hopefully that's a good background, gives you some idea about my perspectives. Now musings, as I write down the definitions here, are contemplative. It could be a lot of things, musings. Things that you think about, you know, I do think a lot about this field a lot of times, just in ruminating about what's the next steps, what can we do, where can we go forward. So I have a few topics I just want to raise. Signals of opportunity, the thermopause, and electromagnetic energy. I feel like I'm in Jeopardy or something, but I'll talk about these things. So if you permit me to muse on about these things, signals of opportunity. For the past quarter century, I feel this community has been buoyed by two primary technological developments that we had not nothing to do with, but we had no say in over how those systems were being developed or used. They had a completely different purpose. And I could add magnetometers to this as well. It's just that I'm not a magnetometer person, so I didn't really put that in there. But Teresa, I got you. So science-grade accelerometers were used for geodesy missions, right? They're using for gravity missions. They're also on magnetic field missions. But they had this annoying signal that was in their way, which with regard to the drag of the atmosphere that they had to deal with. GNSS, obviously, we all know we're getting millions of Pierce points a day, and those were not intended to study the ionosphere directly, but you know, so we've done that. And I would say you should give all ourselves credit for being innovators to take signals that were not intended for us and to exploit them to the point that they have become critical members of our community. And we've drawn people in from those other communities because of our interests. People didn't even realize that this could be a potential use of their mission. And that's helpful for missions because missions need to have those external other reasons to exist. And so I think we should all credit ourselves for that and continue to move forward with the innovations with those signals. I also think we're like one of the best recycles of data that's around. We've recycled, we've told, don't throw that data out, we're going to reuse that, repurpose that for things that were not intended by you. And we've done that in a very productive way. It has helped us with the lack of missions that we've had over the years, that having space observations, and it's been clear why these become such an important resource for us. They provide global distributions that we can't get from our ground-based facilities, so it's been great. However, in addition, we should continue to work these things, but in addition, we need to pursue comprehensive IT measurements to advance the field. There's no question. A measurement of plasma of TEC by itself is informative, but it doesn't get us over to where we need to understand why that TC is structured the way it is, or a measurement of neutral mass density by itself is not sufficient, and so we really need to work that. Another musing I have is this thing called the thermopause, which, okay, so I've been in the field a long time, and we were doing so well with the atmospherics, when we go from the troposphere to the tropopause, we go to the stratosphere to the stratopause, we go to the mesosphere to the mesopause. I don't know what happened, but we ran out of steam and we said, okay, we're just going to call it the thermosphere. We're just, and I'm sure it's something in the history of whatever came along, but it really is. This is a thermopause. It's different than the lower thermosphere. I know the lithosphere people have the same issue with the mantle because there's an upper mantle and a lower mantle, and they have to always distinguish it. And we kind of are running into this. It's not an issue for us. We kind of know what we're talking about, although sometimes I'm not sure. Sometimes we got to be clear about what we're saying. But this particular layer, this thermopause, is the outermost protected part of our sensible atmosphere. When I say sensible atmosphere, what I mean by that is that the same Navier-Stokes equations that can be used to describe fluid flows of the tropospheric weather are the same sets of equations that can be applied up to the thermopause. Above that, this is where the sidewalk ends, and we have to start worrying about all of this ballistic trajectory, exospheric type behavior. And so it's the hottest region that we have in our entire atmosphere. I believe we also have the same problem that the corona has with the sun. The solar physicists have done a great job of calling that one of their great challenges is to determine why the corona is so hot. We have a similar issue, and I'm going to go through that with you and show you where that that issue lies. It's also operationally, as we know, with LEO becoming a very hot region for satellite system operations. And I've just listed here a few things that are different. Now, this is what's different about the upper thermosphere from the lower thermosphere. And high viscosity is what gives us these uniform wind flows with altitude. Highly forced by a mobile plasma. In the F region does transport and move, and that's different than in the E region where chemistry really abounds. Highly responsive to energy, local and remote, and in that regard, due to the lower heat capacity of the less dense upper thermosphere from the lower thermosphere, it can respond rather quickly and dramatically to change. Highly diffusive, dissipative, conductive. I mean thermally conductive. It's not as electrically conductive. And then also just unique chemistry, like the beta chemistry that happens in the F region, between the F region and the upper thermosphere, and horizontally structured domain. And so, and highly variable. And so that's something, I always find it interesting that we don't call it the thermopause. I'm not sure if that, I was thinking about writing a paper, I might, because I think there's some interesting things to raise. So, electromagnetic energy. I felt compelled. I mean, I was almost not going to talk about joule heating at all. But I felt compelled. I know that people know that I've done a fair amount of work in joule heating, but I'm just going to introduce, like, we have to be careful. I think we are the experts in this field. We need to establish clearly what our definitions are. And we're not quite doing that. And I think we need to sit down as a group and agree to the definitions of which we define Poynting flux, joule heating, ohmic heating, frictional heating. And even don't forget about momentum transfer, because we keep thinking about direct heating caused by this, but the winds are moving, and they're not moving just due to the pressure gradients generated by the heating. They're due to the ions moving as well. So I did have one of the reasons why I didn't do this is because I did give a tutorial lecture in 2017 that you can view, which is great. They save these things, which is awesome. But also, I was, if you want to see a stressed out professor in 2017, go check that out for entertainment purposes if you'd like. Because it was, I looked at that recently, I'm like, oh my God, you just look disheveled, I don't know. So MI coupling, missing electromagnetic energy flux, those are key concepts. We have to make sure we get that right. But I want to start to introduce this idea of entanglement, IT entanglement. And in that regard, it's all about transformation. You know, we have these fluxes coming in, but what's really happening in the IT system is that energy is being transformed into some other form of energy, and we're trying to figure that out. And that's where I want to start to talk about entanglement. And so I'm going to introduce to you a concept that I've been kicking around and working with the GDC project office and science team, because I believe that entanglement might be a fair term for the types of things that we're trying to achieve. I know that some of you might know about quantum entanglement, and I'll connect it a little bit to that as well, but let me try this on for size. Before I could do that, I wanted to give a little bit of a history of the IT science, because it helps us kind of remember and connect with what people have done really over 100 years ago in the discovery of the ionosphere. Really, the ionosphere, in a way, was postulated by Kennelly and Heaviside that there must be an electrified layer up there in this high part of the atmosphere. Marconi in 1901, getting the transatlantic signals, really indicated that that thing does exist. And then Appleton, along with Tuve and Brett, they worked on radar solutions. They worked on radar waveforms. They worked on radar reflectivity off of this electric layer. Appleton received the Nobel Prize in 1947, a very readable, you should read it sometime, it's very readable. He talks about how he discovered the F region, and he called it the F region because you had the electrified layer, so that's E. Then they found there was something higher, so that's F, and then they found D, the D region as well. And it's amazing we still use that today, but whatever. It works for us, but it doesn't work for anybody else outside of this room. So that's something to be careful about. But very good. But I also want to recognize Sidney Chapman. If you have not seen anything on Sidney Chapman, The mathematical theory for non-uniform gases is a treatise on how to deal with our type of problem in a mixed neutral and plasma environment. It's quite amazing what he accomplished over his time. And of course, there's been a whole history, progression of this field. There could be lots of other pictures on here, maybe your picture in the future. And I think that the thing about this is that we've moved through these eras. This is our eras tour, we're moving through these eras discovery, connections, characterization. And I feel like we've done that over the past years through the space age, the early missions, all these great movements. But I think right now, and that's what the line, this row right here, is right now we're really, really trying to figure out the causation of all of these things that we've observed for many years. And that's where I think we're in the realization of IT entanglement. I think that's where we're moving into, where we need things we didn't think we needed before, and we need to collaborate and work together in order to achieve that, to ultimately reach our comprehensive future goal of being able to predict this complex environment. And so we all know that the IT is strongly driven. It's a nonlinear dynamical system, which are really interesting things to study as well. They're dependent on the flux convergence of external drivers, but also on the transformation processes that occur within. And this diagram is trying to capture some of that. Again, it's from the GDC project office. Thank you, Doug. And it's trying to capture that. And so there's fluxes that are constantly transferring between but the system we're interested in, of course, is the thermosphere-ionosphere. And so if you start to categorize all the various fluxes, influxes mostly, some outflux as well, if you try to characterize all of these things, what you're reliant on is that you have a representative measurement of what that flux is. And that flux can be spatially, temporally, spectrally diverse, and a difficult measurement, difficult in its own right just to measure that flux. But the thing is that flux has to converge in the IT to be important for the IT physics. So let me just give you an example, and that's, that equation didn't come up well, but that's just basically your general continuity equation. What I was saying was that this should be a divergence of flux here. And that's important. It's the convergence or divergence of flux that causes the transformational changes that happen in our domain. So let's take the spectral, solar spectrum irradiance as our photon flux coming into our system. Well, first of all, we can get rid of more than half, the majority of the solar spectrum, because all of that is just passing right through the thermosphere-ionosphere. None of that is converging into our domain. It's just moving on into to the surface. The key area for us is this vacuum ultraviolet, the EUV and FUVs. And this is the spectrum here in blue, and this is the variability of the spectrum, and obviously we're also in the most variable portion of the solar spectrum. But the key is that energy is converging, and it's also converging at altitudes throughout the IT system that varies and dependent on the state of the IT system. And so what you'd like to have is for every flux element that I was listing there, you want a spectrum. You want a full, complete spectrum, and you want to know which part of that spectrum is actually being impacting the IT system. That's a challenging endeavor and something we continue to work on. And so when looking at the IT system, you see all these inputs and fluxes. I would call coupling to be associated with the magnetosphere, the terrestrial bodies. But internally, there's a process that are happening between the ionosphere and thermosphere. You could call that coupling as well, but I think it's deeper than that. The ionosphere-thermospheric system is entangled. And let me provide you with the definition of entanglement that I'd like to share with you today and see how things resonate. But I look at it as a collection of neutral and charged particles interacting and sharing spatial proximity. That's the key. And it's in such a way that they share that space that a state of one group cannot be described independently without the information of the other state. And that includes spanning large distances. That is, our system that we work with. When we work with magnetosphere-ionosphere coupling, they're not occupying the same spatial proximity. And of course they're coupled, but I would argue that they wouldn't be necessarily entangled. And I feel like this is maybe something that might help in your thinking going forward of how we might try to advance the field a bit, is to kind of introduce this type of thinking. So let me give you a couple of examples, and I've got to be careful on time, so I won't run long. I wanted to give you an example of what I would call entanglement. So here's an NCAR's high-GCM numerical simulation. It's neutral temperatures and winds at 400 kilometers, low activity. And what we did was, and this is from a paper that Vicky Hsu, one of my PhD students in the past, did, where we looked at viscous drag, and we toned down, all we did, everything is the same, except all we did is we took the ion drag term in the momentum equation, we kind of toned it down a little bit, and we said, let's have viscous drag be our sole drag source for the thermosphere. So this is just the thermosphere momentum equation being modified by reducing the drag. And we see that we have, the day side is over here, the night side is over here, and we have a wind system that sets up due to this process that goes from day to night. If we then reintroduce viscous drag, ion drag into the simulation, nothing else has changed. We have not changed the energy input flux. All the fluxes that I just talked about before are the same. What's changed is that we have a term in the momentum equation that has now altered the energy equation. And that's the tight entanglements that we have between momentum and energy transfer, as an example, is that now we have a temperature enhancement that's much higher in the day side and much cooler on the night side. And we'll see when you look at the differences between just the day-night gradients, it's about 150 K difference. When you include ion drag, it's like 400 K difference. It's a major, major change in our temperature when in fact the energy inputs have not changed at all. It all had to do with the energy content within the system. And a lot of that has to do with the circulation processes, because all we did was change momentum term. It affected heavily the energy term. And I know many people who are doing data simulation see the similar kinds of things. They put certain data in, everything adjusts accordingly and changes the outcome. And so I wanted to use this as an example to just indicate that we've got to get some of this right. Now, one of the challenges we have is how do we know that the model's actually right? The TIE GCM has been around for a long time, and it's been an impressive development. It's gone through a lot of different evaluations. And it's not, it's just like EMSIS. Well, I don't know, it's not duct tape, but it's, but it has a lot of we go all through the same processes because we don't know if it's right. We need the observations. And here's just an example of, okay, what observations can I use to kind of test to see if the model's right? And let's use a satellite orbit, because we got lots of those now, and we got a lot of really good data coming out of those satellites. Can we look at the track of a satellite and say, okay, how does it perform if it flies through an atmosphere that's composed of different models? So these are different models, JB08 and DTM and EMSIS and HASDEM. And these are the different densities that they produce. Now this is because the orbit is flying at about 500 kilometers. We're seeing about 16 cycles of day-night, day-night, day-night as we fly through a 24-hour period. So this is just a 24-hour period. And what we do is we just look to see how does the true orbit compare to the orbit that would be produced if you flew through this particular kind of density structure. And sure enough, as time progressed, the orbit, and this is the in-track, so what happens is now the satellite is at the right location, and then the satellite starts to lag in all of these. The satellite starts to lag behind the true location of that orbit, suggesting that these densities are too high. And unfortunately, EMSIS is doing worse out of all of them. But to defend EMSIS, these others are seeded with information. HASDEM has already used 70 calibration satellites at this time to put itself closer to what the actual observations are. So it's EMSIS is going in cold, where some of these are already seeded. So got to give some credit there. The next step, one thing you might say is, well, let's scale these things and get them to get to where this has gone from what was hundreds of meters to just a few meters of residual positioning based on scaling factors that we introduce to adjust the densities. And now you can see that most of the all the models are kind of lining up close to each other, and we're seeing things that are really, really small. A few meters it starts to get into some other uncertainty effects. But these scaling parameters are huge, 40, 50% change. And not like you could say, well, if they all knew what the answer was initially, maybe that would be better. But look at the range of variability you have just between the models themselves. This is a baseline, just we need to up it, we need to lower it. In this case, we needed to lower it. And those are appreciable changes, which really is saying that we're not really getting our density structure or our temperature in the thermal pause proper. We're not getting that right. And the physics models aren't getting that right. So something just as fundamental, as simple as that, we're not getting right. And it's because it's not as simple as saying, if we get the photon flux right, we'll get the temperatures right. It's not true. You've got to get the circulation right. You've got to get the composition right. You've got to get the ionosphere right. So there's a lot of work ahead of us. And then add some variability to this. Add a storm. And here's a plot. This is an orbit from accelerometers flying along. Here's the latitude. And this is just the change in density from the quiet. First of all, the quiet still has a 50% variability in itself, even when it's geomagnetically quiet. This is from the St. Patrick's Day storm of 2015. And as the storm progressed, the orbits were experiencing factors of 400% change in the initial density of 400 kilometers. This is a challenge, and we need to understand how those energy inputs. Now the flux is changing. Now the flux is really important to quantify, and the response is clear. It's dramatic, and it has consequences. And I think that's an important part of our field now. Recognize those consequences. Don't let it necessarily drive our decision making, but it is an important part of our field to contribute to the societal dependency that now lies within the low Earth orbit that we study. Okay, so ultimately we want to get to this global IT prediction. We want to get there and be able to predict this system to further advance our capabilities. Hopefully I've convinced you that we are in an entanglement realization, and that we're observing and interpreting the IT system requires multi-property, multi-point measurements, same time, captured to capture the state of the system. And so we need to have all of the properties of the plasma, all the properties of the neutrals together in order for us to advance that. I absolutely see that the only way we're going to do that is through GDC and dynamic. I do agree that the organization of ground-based facilities that are now coming together, where they're bringing in more in the neutral measurements as well as the plasma measurements. The exciting thing with iSCAT-3D coming online in the near future are great. The daisies are great. But I think that to really elevate it, we absolutely need these missions. It's exciting to see the dynamic phase A's being selected. I think that's really awesome. And so we'll continue to press on and be positive and be energetic and be forthright about what we need to go forward. Just a plug for another exercise that we went through is this Lotus working group. John, I forget in Lotus. I don't even. ESA, NASA, lower thermosphere, ionosphere, science. Thank you. We've been doing it for 2 years. I think I would remember, but we just keep calling it in Lotus for so long. But this is a pursuit to look at the dipping down into this highly conductive lower thermosphere region where we actually can look for currents and the behavior of currents and how currents can impact our system as well as systems outside of this domain. And so that's been a really fun. These things are fun. It's challenging We spend a lot of time, and it's fun and sacrifice. You just end up spending your weekends, you do these things, but you all know that. You do that with your own proposals and everything like that. It's cool to get onto these higher level discussions. I really enjoy those kinds of things. And then, of course, the collegial nature of it all and everybody interacting and you know, is really a fun part of the scientific exercise that we like. So just to close, and I think I'm pretty good on time, so I can pontificate a little bit. Just on the closing remarks, one is try to stay one step ahead. And it can feel like all hell is breaking loose behind you. Stay focused, you know, keep your eye on the road kind of thing. We will help you do that. Don't feel like you're alone in that process. We will help you do that, and you know, we all want to see you be successful in your endeavors, whether it remains to be within CEDAR or others. But you do have colleagues who care about you as a person and about, you know, you as a professional and achieving your successes. Another is planning is everything, and you know, here I just put the CEDAR document, but I understand that there's a discussion, and I think I'm supposed to talk about it tomorrow, about the fact that maybe a new plan might be in order. And I'm fine either way. I think the important thing is that you perform the planning, and that planning is always an ongoing thing. It's an Eisenhower quote, we know, but it is always a thing that we should be doing. Whether you act on that plan, or obviously, look, we're in a field. It's funny, like you think about the side conversations that are happening at this meeting and other times, worried about budgets and everything like that. I have to say, it's been, you know, I've been in the field for a long time. It's a constant, and so you have to fight for your field. You have to. It's not going to come to you. They're not going to. And when you propose $1 billion mission like a GDC, you better be prepared to battle for that. And I think that you know, we're ready. We're hungry for this type of activity, but we have to fight for it. And so everybody contributes. You know, you may feel like, how do I just continue to help and support, and you know, do what you can to see the field advance in ways that will be most you know, most beneficial for everyone, not just yourself. It's good to help yourself, but you know, sometimes you have to sacrifice. I appreciate Chris and all the times that I've sacrificed in the you know, away from family and things like that, and you have to balance that too. Don't sacrifice your family to the point of irreparable. You know, you really need to balance yourself. But again, we're here to help you with that too, because we've gone through it and we can help you with that. So with that, I'll stop, and thank you so much for your time.
Thank you, Jeff. A very inspiring talk. Another clap, perhaps, for Jeff. And I think we have time for a couple of questions from the audience or comments.
Aaron Ridley.
Yeah.
All right.
Okay. So, so in thinking about like your career as a whole, when I look at like my citations, I see like my #1 cited paper, and I'm like, okay, that's okay. But then I see citations that are like way down in the doldrums, and I think, boy, it would be nice if those were actually recognized.
Right.
In your career, what work do you think that you have done that you wished was like more, not necessarily recognized by the community, but like you thought, oh, this is a great piece of science, and people just didn't respond to it as much as you would hope?
Wow.
I asked the easy questions.
That's a great question, Aaron. I think that's I'm not a big promoter. I think a lot of us are not big promoters of our work. We kind of write a paper and expect people to say this is, to have the other people promote it, right? That's where the citations come in. You try to review papers and let them know and remind them of papers that you wrote and you reveal yourself as a reviewer, which is fine. But we tend not to be good self-promoters. And I agree with you that there are works that the sweat equity that went into a paper is really hard to tell in the electronic form, because the sweat on the paper that you were working at is definitely there. And so it's I think I'm just more, I don't have that, I do care, but I don't, the body of work, I really just enjoyed the people that I worked with and the collaborations that came from that. Yeah, I know we're faculty, so there's citations and that's how they judge us, which is really sad. But I think that I just find it, I mean, I really enjoyed the joule heating work. I really think that some of that stuff has been things, and there's some things in there that I wish people would definitely look at a little closer. I really enjoyed the PMC, the polar mesospheric cloud work. The thing about my research, and I've always found this to be a little bit, is that I don't spend enough time in one field long enough to drill down into it to be like, oh, that guy, like he just knows all that stuff. I've definitely have been like, okay, I'm done with that. I'm over here now, and I know some of you in the community understand, like the ISR guys. I know, I worked with you all for a long time, and then I'm like, oh, I'm over here now doing satellite drag work, but I wholeheartedly value that community as being an incredible community of researchers. The same with the LiDAR folks that I worked with for so long. So Aaron, I don't know, it's a long answer to kind of dodge your question. but yeah, that's kind of where I'm at. It's a great question. I think Rob Pfaff has a question, but because he's always got something.
We probably have time only for one quick question.
Oh, Roger. That'd be awesome. Hi, Roger. Haven't seen you this week yet.
Yeah. Great talk, Jeff. Thanks so much. So on your terminology of thermopause, can you define the difference between thermopause and exobase?
Oh, yeah, sure. In fact, it was great to see Sarah Luchin being awarded the prize for her poster, her CEDAR poster on basically thermosphere-exosphere exchange, and did a great job on your poster. And I should also credit Eric Sutton is doing a lot of the work to explore that space. And so we're in the process of actually doing a much better definition for exopause, really exosphere-thermosphere exchange, because there's a process of exchange that happens across that boundary. People use the mean free path to scale height as kind of your Knudsen number representation for your exobase definition. We're changing that. I think, Sarah, you would agree that that's not quite sufficient. Exospheric temperature bothers me. That we use in the thermopause, we call that the exospheric temperature. That is, for a new person coming in, they're like, what? Why are we calling something that's in the thermosphere an exospheric temperature? An exospheric temperature is going to be like a kinetic temperature. It's not going to be a thermalized local thermodynamic equilibrium state, So that's another one I rail against too, is exospheric temperature. Yes, it's asymptotically going that way through that profile. And so, to me, thermopause is defined at the place where the slope of the temperature is zero, is infinity. And the exobase is in our domain more than we like to admit. We're using models that probably are using continuum mechanics at altitudes where they shouldn't. And that's true for the time GCM, TIE GCM, and GITM, and all these others. And we need to pay attention to that. A simple diffusive equilibrium extension of those models into the exosphere is also not sufficiently representative, and Sarah will be publishing that work in the coming months to demonstrate that. And so, yeah, it's a good one, Roger. That's definitely one we need to do a better job of conveying. We get a little bit of acceptance. We accept some of these terms. We accept question those terms. New people, students in the field, question those terms. Question them and make sure that they make sense to you. So, yeah, thanks, Roger.
I think we have one quick question from online.
Yes, great point about definition of Joule heating, etc. There are good reference out there, like your 2004 appendix. What else should we do to get on the same page?
Yeah, that's a good question too, right? How do you terminology is really important to me. I talk to my students all the time about being clear about your terminology. Terminology is really the communication. If we're not on the same page in terms of our terminology, we're in trouble. We send a mixed message. We can't send mixed messages. We have to be really clear. We are the experts in the field. Let's make sure that we can communicate properly. And so the problem we're having, this is we can have a whole session. Aaron, maybe we should have a whole session because Aaron, when you talk about Poynting flux, sometimes we don't know what to do with Poynting flux from a modeling perspective. We know it's really important, but we don't know what to do with it. But we need to define it well. And then Joule heating, frictional heating, I'll tell you right now, my preference, frictional heating. And then it's what it, yeah. There you go, Brian. And it's neutral frictional heating, which is different than ion frictional heating, which is different than electron frictional heating. And I have seen papers recently that have been using, and it's awesome. Joule heating is also a fine term, but be real clear about what you're trying to say. Joule heating is only about heating of the neutral gas, or really the mass average gas, which turns out to be the neutral. And so I'm losing track of what the question was, but I'm definitely passionate about terminology. We should be good about it. Maybe we should write a paper on it or some declaration of it. But I was just the Lotus team. We were working on this. And in the document, we have Joule heating, frictional heating, ohmic heating. And I was just like, we can't do this. We have to figure that out. And that's even within our own group that all know this stuff too. So, and I'm sure it's true in other facets of our community. Whether it's spread F is that a good word? There's a lot of terminology that we could probably clean up and particularly when we draw attention to our community from others outside our community. You want $1 billion mission, you better be real clear about what you're trying to achieve. And so, so that's on us. So thanks.
Okay, I think we
right.
should probably move on. Yeah.
Thank you very much.
Well, thank you, Jeff, for a really great talk. Are you sure it's been 37 years?
I know, right? I keep doing the math.
Feels like 10 or 15 tops.
Yeah, Mark and I have been together for a long time with this kind of stuff. It's crazy.
Anyway, one of the really important things that we get to do is to recognize these contributions. And so, we have a certificate here to recognize Jeff for his selection here and for the talk he's given us today. And this, I get to hand this to Jeff, but this is not an award from me. This is not an award from the CEDAR Science Steering Committee. This is an award from CEDAR, from all of you, to recognize Jeff's contribution. And the thing I really liked about Jeff's talk, CEDAR is many things. CEDAR is the science that we see here and the interactions and the discussions. But to me, CEDAR, the aspect of CEDAR that appeals to me is the way that CEDAR can build a community and support a community and help us explore new ideas. And I think Jeff did a really great job of that. And so I thank you for that. And for the students here, or for all of us really, one slide that caught my attention in Jeff's talk was his slide where he had a bunch of great ones up the top who've made big contributions to our field. And down in the bottom right-hand corner, he had a little square that said, your picture here. So, Jeff is our distinguished speaker today, but others in this room will take the same role soon, and students in this room will be taking the same role in another 37 years or something. But so thank you, Jeff. That was a great talk, and I appreciate it.
Okay, this concludes our morning session. Let's thank again all the speakers.